everyone, welcome to another two-dimensional kinematics problem. This one on relative velocity example 1. Huck Finn walks at a speed of 0.50 meters per second across his raft. That is, he walks perpendicular to the raft's motion relative to the shore. The raft is traveling down the Mississippi River at a speed of 1.60 meters per second relative to the riverbank. What is Huck's velocity, speed, and direction relative to the riverbank? So before we actually dive into the actual problem, there's a couple things I want to show you first about how to solve relative velocity problems in general. Okay, so the next thing is this problem actually gives us a picture. It's just a visual to represent what's given in the problem. Okay, you've got the river, the current's going towards the right. Huck is walking across his raft perpendicular to the direction of the river current at 0.50 meters per second. And another thing I've done here is define the positive direction. Okay, so because we're working with a two-dimensional problem here, I'm going to let positive be to the right and up, and I'm actually going to label right as x and up as y, so positive x, positive y. This will become really helpful later as we define our velocity to be a vector with two components, x and y. Okay, now, with any relative velocity problem, the first thing you want to do is define your three objects. Okay, generally speaking, there's only going to be three. Okay, so in this case, our three objects are Huck, the bank, and the raft. Okay, so in the question, they refer to the bank as the shore. Same idea. Okay, then you want to abbreviate each one. Okay, so for Huck, I'm going to represent him as H, the bank as B, and his raft as R. Okay, so how do you determine those letters? Well, it's in the problem itself. Okay, so you see here, Huck Finn, obviously he's the one walking, so he has to be one of the objects. He's walking across his raft. Okay, so there's another object, and it's relative to the shore. So the bank has to be the third one. Not to mention, the actual question is asking you for Huck's velocity relative to the bank. Okay, so there we go. H relative to B. That's what we're looking for. Okay. Now that we've established our three objects, I want to show you the general formula for solving relative velocity problems. Okay, so whenever you do a relative velocity problem, let's say your objects are A, B, and C. Let's just say, just to make the formula. If you're looking for the velocity of object A relative to object C, this is how you write the formula. It's velocity of A relative to B plus the velocity of B relative to C. And we got to make sure we put our vector symbols there because this is vector addition. Now this is how you write it. You see how we're looking for VAC? The reason we have to write the right-hand side like this is because the two inner letters cancel. Okay, so the two middle letters need to cancel. So they must always be the same. I hope you guys can see that. If not, I'll just reiterate it again. AC is what we're looking for. So A has to be on the first subscript in our addition here, and C has to be the last one. And the two middle letters need to be the same. So imagine them canceling out, and you're left with A and C. Okay, so with that in mind, let's take a look at what we're looking for in this problem. We're looking for Huck's velocity relative to the bank. Okay, so we're looking for V Huck relative to bank, VHB. Now, I can already create the formula without even knowing my other knowns. If I have an H and a B here, let me just write the next two parts. I'm going to have a V here, and I'm going to have a V here for velocity. The first letter of the first V is going to be the first letter of this one, H, and the second V will have its second letter as B. Okay, so now what is missing from here? We have our H, we have our B. What we're missing is R. Okay, so R is going to go here as the second letter in the first term and as the first letter in the second term. So VHB equals HR, VHR plus VRB. Okay, this is how you construct these kinds of problems. So now we've got our equations, and let's just make sure what these values are relative to the question. Okay, so Huck relative to his raft, well, it tells you in the question he's moving at 0.5 meters per second across his raft. And the raft relative to the bank, well, it tells you the raft is going down the Mississippi River at 1.60 meters per second. Here you go, relative to the riverbank. So we have those numbers. Now you got to be careful here because you're not simply going to plug in 0.50 and 1.60. In this problem, velocity vectors are given in terms of an x component and a y component. Okay, and we're going to add the components together as vectors. That means x gets added to x, y gets added to y. Don't mix the two up. Okay, so let's continue with this. So we've got our statement. We've got VHB equals VHR plus VRB. Now we're going to start plugging in our values. Okay, so VHB equals, these have components, so I'm going to draw brackets, put a comma in between, plus, again, brackets, comma in between. Okay, Huck relative to his raft, based on our picture, take a look. Huck is moving in this direction. He's moving in the positive y direction. The river current's going in the positive x direction. Okay, whereas for the current, it has no y direction. Likewise, Huck on his raft has no x direction. Okay, so we're going to have to input those numbers as is. All right, so Huck relative to his raft, x component is 0, y component is 0.50 meters per second. The raft relative to the bank, the x direction is 1.60 meters per second. No y component there. Okay, so when you're adding vectors, you take the x values, you add them together, and you take the y values and you add them together. Okay, so overall, your vector is going to have an x component and a y component. 0 plus 1.60 is 1.60 meters per second. 0.50 plus 0 is 0.50 meters per second. So this is the vector Huck relative to the bank. Okay, so of course we're not expressing it like this in our final answer. We want to express it in terms of having a magnitude and a direction, okay, not simply as the xy components. So let's solve for the magnitude of Huck relative to the bank first. Okay, so for our magnitude, remember, if you put the absolute value symbols around a vector, this implies that it's simply the magnitude, or you can just drop the vector symbol and say VHB. So the way you take the absolute value, the way you find the magnitude is by adding the sum of the squares of these two terms and then taking the square root. Okay, so square root of 1.60 meters per second squared plus 0.50 meters per second squared. Okay, so velocity of Huck relative to the bank, if you calculate that, it comes out to 1.68 meters per second. Okay, so let's continue. That's our magnitude. Now we still need to find the direction. Okay, now for direction, we have to look at this in terms of a vector problem. So remember, you've got the velocity of the raft relative to the bank. Okay. And then you've got that's going at 1.60 meters per second. Then you've got Huck relative to his raft moving perpendicular. So Huck relative to raft is 0.50. And when you add those two vectors up, you're going to get Huck relative to the bank. So remember, the tail of the first vector to the tip of the second vector. So this is velocity of Huck relative to the bank. And the angle we're looking for is the hypotenuse to the initial vector here. Okay, now we've got our theta, we've got our VHR, we've got our VRB. Okay, so since we know these two opposite sides, although we did find out VHB, remember you don't want to use that in your calculation for theta. In case you did something wrong here, you don't want the error to propagate down here because you'll just get more marks off in that respect. Okay, so tan is what we're going to use since we were given opposite, we are given adjacent. So tan theta is equal to 0.50 over 1.60. Okay, so if you take this ratio, it comes out to be about 0.3125. So we have to take the inverse tangent of both sides. So inverse tan of 0.3125. And when you calculate that out, you're going to get theta to be 17 degrees. Okay, now 17 degrees, look at that. What is that relative to this angle? Well, this is relative to the riverbank because remember, this is the direction of the current. So therefore, this line here represents the riverbank. That's relative to where it is. Okay, so that's it, guys. You found your magnitude of Huck relative to the bank. You found the direction. So we can say that therefore, the velocity of Huck relative to the bank is 1 point. Now, how do we do this for sig figs? We've got a 0.50, that's 2 sig figs, and a 1.60, that's 3. So we want to answer this to 2 sig figs. So instead of 1.68, let's do 1.7. Okay, 1.7 meters per second, 17 degrees relative to the riverbank. Okay, and that's it, guys. That's it for this video. I hope you enjoyed it. I hope you understood how to do these relative velocity problems. I'm going to be doing several more relative velocity problems, so stay tuned for future videos. And if you guys enjoyed the video, be sure to click that like button and subscribe to this channel so that you never miss a video from me. Thank you, guys, and I will catch you in my next video.